Just double check. Okay. Let me just get some water and then we'll start. Let me see. I think I might want to also. This paper, which is I'm one of its authors. The paper is about evaluating the interpretability of sparse autoencoders and similar replacement model architectures without relying on generating explanations. This is kind of a follow-up on a previous paper where I'm also an author of, where we were trying to evaluate the interpretability of sparse autoencoders, and a step to generate to evaluate that interpretability needed some the generation of interpretations of the feature. So I'm going to start by explaining that, and then I'm going to move to the other paper. So the idea with a sparse autoencoder or a transcoder or a crosscoder or any of these new architectures that are meant to decompose the activations of models is that they are basically trained on a bunch of text, and they're trained to reproduce, in the case of sparse autoencoders, the activations of the model. And then if you want to see what each feature of the SAE means, what people normally do is that they collect activations, and in this case, these green words are the words where this feature is active, and you see that in some sentences the feature is not active, and even in the sentences where the feature is active, there's a bunch of tokens where it is not active. And basically, you collect these sentences, you select the ones where the feature is active, and then you show them at the same time to a large language model, and you ask it to find the patterns. And so in this case, for this feature, the large language model said that it's about prepositions and verbs denoting directional movement or change, blah, blah, blah. And then if you want to know how good this explanation is, there's some different scoring methods that people use. One of the original ones was simulation, where you'd have the explanation, then you'd have a sentence, and you'd ask the language model to predict the activation of that feature on each token, and you do that for a bunch of sentences, and then you compute the correlation between the true activations and the predicted ones, and that's called simulation. In this paper, we proposed simpler versions than simulation. One of them is detection, where you're just asking the model, in this sentence, is the feature active or not? And for that, you show sentences where the feature is active and sentences where the feature is not active, and then you can compute the normal recall, precision, etc., F1, and those numbers can be used to tell how good an explanation is. But these numbers are related to the explanation, and they don't actually tell you how good or how interpretable the SAE feature is, because when you're this middle part of the process, the part of generating interpretations, can just be flawed for one or multiple reasons, where maybe your prompt is not good enough, or you're using some kind of architecture that requires a bit more consideration, and your model is not that smart. So actually, by doing this, let's say, 3-step process, the scores that you get at the end don't actually tell you how interpretable the SAE is. They just tell you how good your explanation generation process is. And maybe the SAE is actually interpretable, but you missed on this step. And so with this in mind, and inspired by other results in the literature, not about interpreting SAEs, but interpreting other types of models, we thought, okay, can you try to interpret the features of an SAE just by looking at the activations, and instead of generating any explanations? So the normal pipeline in the previous paper that I explained is this down arrow. So you collect activations, and then you show a bunch of these activations to an LLM. It will generate an explanation, and then you use this explanation and some activating examples, and you try to compute the accuracy and use that as a metric. Instead, we propose two different methods. Well, we propose is maybe a strong word. These both intruder detection and example embedding were already in the literature, but used in other contexts. Intruder detection is very, very simple. You just show the model 5 different examples, and maybe you show which token. Here I highlighted the tokens in black, but when you show it to a model, you do it in a different way. But you show to a model, let's say 3 examples, 5 examples, a certain number of examples, where all of them are from a feature, and then except one, which is just randomly activates other sets of features. And you ask the model to find which of these examples is the one that is not that's the intruder, right? And so you'd expect that if the SAE or this feature is easy to understand, or it's interpretable, you should be able. The argument goes that you should be able to find what are the contexts where the feature is not active. And if you're shown enough examples to try to suss out the pattern, you should be able to find this intruder. And the other score, which it's similar in nature, but it's set up in a way that you don't even need to use an LLM, but you could, is what we call example embedding. And in that case, you basically have a set of activating contexts, a set of non-activating contexts, random contexts, and then you're given a pair, and you using an embedding model, you have to select if the pair, if this example goes to the first group and this example goes to the second, or the other way around. Basically, in literature, this was called two forced choice, something like that. Two alternative forced choice. So you have two alternatives and you're forced to give one to one group and the other to the other group. And the idea here is very similar to the intruder, is that because these are random examples, and while these are should be coherent examples because they activate the same feature, when giving an activating example and then a random example, you should be able to just pair the activating example with the ones that are the activating examples because they would be similar, while the random example is obviously going to be random, and so it's going to be more similar to the random examples than to the ones that are grouped. And so these were the two scores, these two ideas that we decided to use to try to evaluate these SAEs. Again, the biggest problem with all this approach is that there isn't really a ground truth measurements, right? There's nothing that we can compare these measurements that will tell us, okay, this is a good score at the end of the day, except you'd maybe have a human also look at the feature and try to understand if it's interpretable or not. So this was the introduction. If people have any questions, I think this is a good point to ask because I just explained basically the full methods, and then I'm going to talk about results. So if people want to ask any question, they can just speak or also write in the reading group channel, and I can see it. I'm going to just pause for 30 seconds to drink water.
In your opinion, should we replace old auto-interp with this?
So I think there's a point to still generating explanations, but if you're just trying to measure whether your latent is interpretable or not, like if you're just trying to make those plots, for instance, SAE bench, I would be inclined to not do what SAE bench does now, which does require the generation of an explanation, and do this. Even though maybe you could argue that it doesn't really matter because at the end of the day, like even though the explanation generation part is bad, it's equally bad to all models, let's say. And so if your SAE is interpretable, like you just are paying some kind of a tax, but it doesn't matter because it's the same tax for every model. It's not obvious if that's true. I don't know if that's true. And in fact, yeah, some SAEs, maybe because they have hierarchical structure, etc. This other pipeline, the pipeline that's illustrated here, doesn't capture hierarchy that well, and so explanations will just be messed up, while maybe this intruder detection, which maybe also doesn't capture hierarchy that much, could be a way where the part of generating explanation no longer breaks your whole chain, and now you just have to fix one thing instead of having to account for two things, which I think is important. Because in this case of hierarchy, you probably need to change not only the part of generating explanations, but also the part of scoring the explanations. And so here you would only have to change the part of scoring because you're not generating explanations.
Mm-hmm. Okay, so if you're not generating explanations, I guess like, how does like interpretability as a score kind of relate to monosemanticity, in your opinion?
Yeah, I think that's a good question. So people when they were introducing sparse autoencoders, they were really pushing on the L0 versus reconstruction loss, like Pareto curve, which was important, and it's still kind of important because we are so far away from actually getting to a good point. But it was hard to push on the reconstruction versus interpretability Pareto curve because we didn't have a good way to measure interpretability, and we didn't even know if we wanted, I don't know if feature splitting is a feature or it's a bug. Like, is this just what it means to be monosemantic? And so having a way that you can try to measure this interpretability without having to generate these kind of nebulous explanations in the middle feels nice. But yeah, I still think that we don't know how to measure interpretability perfectly, and so is interpretability just monosemanticity? I think is still something that it's not obvious what the answer is.
Okay, thanks.
Okay, if there's other questions, people can just. I saw Ben was typing on the chat, but he didn't finish. So
you kind of covered my question in your answer, so I'm good.
Okay. So I'm going to go forward to the next. To the results. I mean, the particulars thing I doesn't really matter. Like, we were looking at small LM, different layers. I think these are kind of things that don't really matter. For intruder scoring, we also did human intruder scoring. One thing about intruder scoring is that it's very easy even for a human to do if your SAE is interpretable, but it's also frustrating because you have to pay attention. Like, if you're trying to actually measure how good the latent is, some latents require you to think about them for more than 10 seconds. And you may argue, do you want this or not? I think so, because otherwise it would mean that you'll only be representing very simple concepts. But yeah, we did intruder scoring with a human, which took more time than the results that we got out of it. And in fact, like the maths, I'm going to skip all of it. And these are the results where we match up a human, which in this case was mostly me, doing each point is a different latent, and on average, each point, the size of the point is how many examples the human was evaluated on, and I think the smallest point means that I saw 8 examples. Yeah. So I saw 8 examples, each with 4 activating examples, sentences, and 1 non-activating sentence, and I had to find out which one was the intruder. And yeah, there's not that many points. I think it's only 56 latents, so 56 points. But you'd see that a human, me, and Claude Sonnet agree in general on whether a latent is interpretable or not, or we are about as good on identifying if latents are or the intruders, which is a good thing. It's kind of important that you do this test, because it could just be, and in fact it must be, that an LLM will just find patterns that in a much smarter way than you, right? And so we wouldn't want that the accuracy of the LLM is much higher in general than that of a human, because it would mean that it would be finding patterns that a human wouldn't be finding. And so that's why we did this calibration. I think it would be cool to do this in a larger scale, but I never had the time to try to organize this. And then this plot is just, if you divide these in a grid, like in quadrants, how does it look like? It's just a discretized version of this plot. But basically, you see that there's kind of a, it's not really lower triangular, but indeed, you could maybe argue that the LLM even gives lower scores or has a lower accuracy than humans, because you see here there's four latents that Claude only got an accuracy between 0.4 and 0.6, while I got an accuracy between 0.6 and 0.8. And in this task, there were only 5 examples, so the random chance accuracy would be 0.2, and so that's what we call like not interpretable, or you could even argue that probably from 0.2 to 0.4 it has a low degree of interpretability. Obviously, these are all made up thresholds, and this is mostly to get a feel on whether humans and LLMs do this task in a similar capacity.
I have a question.
Yeah.
I don't understand your take, I suppose, on why it's bad for LLMs to be better than humans at this kind of classification task.
Yeah, I think the fear would be that
like if you think about interpretability, right? Like,
yeah,
hopefully interpretability is relevant in the superhuman AI world.
yes, yes,
and it's possible that things are beyond our understanding. So it's not.
yeah. So I think that would be okay if at the end of the day the LLM could distill what it understood to us, right? But here, because
Right.
you're not generating an explanation, if it's just finding these galaxy brain patterns that are not human interpretable because a human couldn't find them, you might be afraid that you're actually not measuring how human interpretable it is, but how LLM interpretable it is, and those are maybe not exactly
aligned.
Yeah. So probably at this point with the LLMs that we have, and like if you use Claude Sonnet 3.5 or Llama 70B or whatever, those are probably well aligned or close enough. But maybe you'd worry if Claude was already much better than a human at doing this task, that if you just use this score to evaluate SAEs, you'd actually yeah, your LLM would just be finding patterns that then when you look at the SAE, it's not interpretable at all, and so you'd just be eluding yourself. That can still happen, right? But I think it's good that that they find basically the same trend, like the kind of features that Claude finds interpretable are basically the same that I find interpretable. Like there's not a point here, right, where I don't see any pattern and Claude finds the pattern 100% of the time. I would maybe be okay with a point here. Sorry, I was not doing here. Now you can see it. Like I would maybe be okay with a point here where I can see the pattern and Claude can't see the pattern. And that just means that, yeah, maybe it's out of distribution or Claude is just not smart enough yet. But if there were a bunch of points here, I don't think I would be happy with this metric that much. Because, I cannot understand what the pattern is here. And in this case, maybe if you ask Claude for an explanation, it could give you one or not that works or not. But yeah, we wouldn't know, and this method just doesn't generate expressions.
Right. I guess it's like, okay, if it was much stronger, we would need something else, and then something else is like a way to distill it into an explanation that we can parse.
Yeah.
Okay, got it.
Yeah, so this was just basically a validation. There's also some other numbers here about how, I think it's before this plot, no, maybe it's afterwards. Was just a validation of how close human scores are than LLM scores, and so from now on it's just LLM scores because it's too expensive to do human scores. Here in this plot, there's still a human score, and I think this is an interesting plot which I'll have to explain. So, can I write? No, I don't think so. I can. So, if you have an SAE and you plot the distribution of activations, it might look like something like this, where obviously you have some examples where the feature is very active, and then you have some kind of, it's not really Gaussian, but you can think of it like as just a peak. And normally this region, even though it's the most frequent region, starting on these activations, probably the latent is no longer that interpretable. And so what we do here is try to evaluate how interpretable the latent is, or a set of latencies across the whole distribution. And here, when we say decile and highest and lowest, we actually mean decile in the normal sense of a distribution, and not in another way that you might think about it, where maybe we just divided these into 10 bins of equal activation strength. This would be a way to do it, but that's not how we do it. We do it in such a way that each decile has the same number of examples. So maybe it would be like this, and like this, and like this. And so the decile has the same number of examples, but inside the decile, especially the highest decile, because there's so few high activating examples, it's probably going to have a big range of activations. And the same thing on the lowest example. You probably have, like, it's probably going to be a big chunk of low activating examples. And then on the middle, you're going to have a bunch of very similar bins of basically the same activation. And what we do here in this intruder, in this plot, and also
everywhere is that when we're doing the intruder detection, we are sampling 4 examples from the same decile. So all 4 examples are from this decile. And then the intruder is from a non-activating example. So it's not in this distribution. It's a 0 in the distribution. So the distribution is normal like this, and then there's basically a delta Dirac at 0, because most features are not active at any given token. And so here we are just plotting the accuracy of intruder detection as you move along the deciles. So if you just take examples from the highest activating decile, you have the highest accuracy. And this is just reproducing what we expect from SAEs, right? People had seen already that the top activating examples are the ones that you understand very easily. And so this is just a normal result. And then you just kind of see a trail off until you go to the lowest activating decile. But notice that random accuracy would be here. And so even these lowest activating deciles, for some features, you can still understand them, or at least you can still distinguish these 4 examples from the same decile from a one that's completely random. And we see the same pattern for a human. You see that the error bars are much bigger, because in the case of a human, there's just less examples per decile per feature, and so it's a bit more noisy. But you basically see the same kind of trend. And in fact, if we break this down, and I'm going to show you this appendix plot. If you take the features that have the lowest accuracy, then and this is the random chance, right? Their profile looks like basically random on all distribution, and maybe a bit better than random on just the top activations. Then the next kind of features, they look interpretable, or like quite interpretable at the highest activation decile, but then quickly go down, still better than random, but very close. And as you're moving up, this becomes even more evident, where the highest activating example is very accurate, and then it drops very fast, up until the most interpretable features, where now the drop-off is much less pronounced, or looks less pronounced, where you go from like 95 accuracy to like 80 something accuracy, which really shows that maybe there's a kind of sets of features that are very hard to interpret. There's some features that are interpretable, where obviously the highest activating examples are more interpretable than the rest, but they're still interpretable. But there's a bunch of features which are interpretable on the full distribution. Even these examples here, you can distinguish them from non-activating examples, which I think is not. I'm not going to say unexpected. It's not unexpected. I think that there were maybe some evidence that this might be the case, but I think it kind of goes a bit against the grain, where most people were maybe arguing, maybe you shouldn't even look at these examples. Either just look at these examples, or maybe look at the majority of examples, and you can just discard these examples, and they'll never be interpretable. So this was the breakdown of this plot. One good thing that you can do with intruder detection, which you can't really do with the other scores,
is that you can decide for your intruder to be anything that you want. You can even have your intruder be an activating example from a different decile. And why would you do this? So the idea would be that if your feature is completely monosemantic, and this doesn't delete, so I'm going to make a new a new one. If your feature is completely monosemantic, and there's no, so if your feature is just activates on house, maybe you'd expect that all these activations are going to be house. But maybe your feature is a bit more complicated than just house, and it actually is like all kinds of housing. So maybe apartment, maybe shed, maybe mansion, whatever. And maybe the hypothesis would be that there's not really a gradient. There's really not a way to order like the different types of houses, right? Maybe like a mansion is as much as an house as an apartment, and so maybe you wouldn't expect that mansion is here and apartment is here, and so if your feature is this like activates on kinds of places to live, and it's just completely monosemantic, you wouldn't be able to distinguish statistically the different deciles. On the other end, maybe there is a gradient, and maybe there's not an obvious way to sort these kinds of housings, but this feature learned this sorting, whatever sorting it is, and so maybe in fact it puts mansion here and apartment here, and most apartments are here and most mansions are here. And so if that's the case, if you use this as an intruder, you'll be able to distinguish from the mention activations. And in fact, we see that. So if we use as the 4 examples some from the activating from the highest activating decile, and as the intruder an example from the lowest activating decile, you still are able to get much higher than random chance. It's much worse than if instead of a low activating example, it was a non-activating example, which is this point here. You see that here the accuracy was close to 80%, while here the accuracy is only 50%. But it's about the same accuracy as having a lowest activating example and a random example. And as you move closer and closer to the decile that's just before the highest decile, you start approximating random chance. And you can do this for all other deciles, and you see this drop-off, and probably here it would be hard to argue, like all these numbers are very close to random chance, and so here these deciles are very similar, but you always see this trend of going, you can always distinguish from the lowest, and then as you move on to the closest example, it becomes harder to distinguish. And then, I think for me, kind of a surprising result is that this is not symmetric at all. So if you have 4 examples from the lowest activating decile and 1 intruder from the highest, you actually are worse than random chance. And how can you think about it? I think that the reason is that this highest example will probably always find 1 example on the lowest activating that is similar to it, and so the LLM is less likely to use the highest activating example than it would be of random chance. So it's not that the lowest activating examples are completely chaotic and there's no pattern there. There is a slight pattern that still reminisces the highest activating example, and so it basically fools the LLM into picking the highest activating example less. I think this asymmetry was surprising for me at start, but it's not such a stark asymmetry, right? It's very close to random chance, and I don't have error bars here. I expect them to be small enough that, for instance, this point doesn't overlap with random chance. But yeah, the fact that this is not symmetric does confirm that the highest activating examples, well, you also see it here, the highest activating examples are always much more interpretable than the lowest activating examples. And these lowest activating examples, even though you probably can distinguish them from a random example, you cannot really find a pattern between itself if you have a highest activating example. It's hard to know which one is the intruder. So these are the results for the intruder detection. I think the next plot is about about first choice. So I'm going to leave it open here if there's people that were just super confused about all my drawings and like what this decile means and what I'm plotting here. So if people have questions, they're free to ask them now.
On your explanation for why it wasn't actually symmetric, were you saying that sometimes the lowest will be a subset of the highest, but the highest won't be a subset of the lowest, basically?
Yeah, I think that's I'm not sure if I would use those words, but I think the highest always is more cohesive between themselves, while the lowest will maybe have a team, where the highest example fits into that team, and so it's hard to distinguish it from. So it's like the highest example is just more specific, and the lowest is a more general. And so when you have a specific set of things, it's easy to distinguish the general from the specific. But when you have a general set of things, it's hard to distinguish the specific from the general, because the specific is the specific, right? And in the general, everything is the same level of specificity. I think, and I don't know if this analogy is easy to understand, but it was easy to me.
Yeah, that makes sense. Thank you.
Yeah. And so when we do embedding scoring, actually it is symmetric, and it must be symmetric for So here on this side we are doing exactly the same thing, but with embedding scoring, and I'm going to remind you what embedding scoring is. You basically take a set of activating examples, which you call, let's say, your dictionary, and a set of non-activating examples, which is your non-activating dictionary. And here on this picture, they look to be like about the same thing, but in general, these are going to just be random examples. And then you select two examples, one that activates and one that doesn't activate, and these are your queries. And you embed all of them with an embedding model, and you measure the average cosine similarity of this example with this and this, and the average cosine similarity of this example with this group and this group, and you basically just order it such that if this is closer to this group, then this is closer to this group, and is farther from this group, then this one is farther from this group, you order the blue with the blue, otherwise you order the blue with the green. And because of the way that the score is written, it must be symmetric. So if you're sampling from one quantile and all the other examples are from the other quantile, you could just switch the labels on the equation, and so by construction this is going to be symmetric. And you see something that maybe contradicts the previous result, where now you no longer, you no longer see the big drop-off that you saw before. And in fact, it seems like for the highest quantile, you can always distinguish with embeddings from all the other. I said quantile, but I meant decile, which is the same thing. You can always distinguish from the other deciles. And as soon as you go to the next one, now it drops off. And 50, 55 here, this is the area under the area under the curve, and so 50% is random for this metric. But we kind of see the same kind of trend if you stratify stuff. The highest activating examples are always going to be easier to distinguish from random examples, and then the lowest activating examples are going to be a bit harder, and there are some features that are just not interpretable, and so they'll basically have random chance. The worst thing about embedding is that it seems like the Pearson correlation between these scores and the human scores and the other scores from the other paper are quite low. 50 is not that bad, but if you look at intruder detection and human intruder detection as a Pearson correlation of 84, and even with the other scores, for instance, fuzzing, it has a correlation of 74. And for instance, fuzzing and detection had a correlation of 71. And so it is a bit bad that these embedding scores don't actually match the kind of interpretability score that a human would give. Like you would hope that you could use this example embedding as a way to evaluate features much faster, because now you don't need to call an LLM. Normally, you can just use an embedding model, and embedding models, you just do a single forward pass, and it embeds the full sentence. And normally, you can just use a smaller embedding model. So in this case, I tried both with a 7 billion model and a 700 million parameter model, which is much smaller than the 70 billion model that I'm using for the intruder detection. And so, in principle, like the holy grail would be to have this embedding score be very similar to the human scores, because in principle you could just score thousands of features very quickly, much quicker than what can be done now with any of the other methods, like 1 or 2 orders of magnitude quicker, and so cheaper. But unfortunately, that were not the results that we got. We still got the kind of trends that we were expecting, so that the highest quantiles are more interpretable than the lowest quantiles. But these results tell us that and I don't think I have any scatter plot here. No, I don't. But these results tell us that some features that the embedding scorer scores highly, the detection scorer scores low, and the other way around as well. Which is kind of a pickle to be in, because now you don't know which score to trust. And the other thing is that, on average, the embedding scores were much lower than the detection scores. So if we like look here, I don't have this plot and I'm just making stuff up as I remember them, but it would basically be that the curve of the LLM, the scores of the LLM would be like this, right? Yeah, like this, which, well, you can still calibrate to what a human gives, right? But you'd prefer it to be like closer to like exactly a straight line. And yeah, we are now reaching what's this? I just skipped this plot, but I think for intruder detection, this is just also a nice table to look at, to show that if you remember here, the R squared between human and an LLM, and again, this is only 54 examples, is 7. And even between LLMs, you'd have R1 scores that are lower than with the human. So in a sense, Llama 70B agrees more with the human than it does with Llama 8B. But that's just because Llama 8B is a bit dumb, and you see that it also doesn't agree well with the human. But you have these stronger LLMs, for instance, at the time of writing this, Claude Sonnet 3.5, which agrees a lot with the human, like the Pearson correlation is 0.84, and it even agrees more with Quen. And so this kind of metric is, intruder scoring is kind of stable with models as long as you use a strong enough model. Interestingly, Gemini Flash 2.0, which is about the same price as Llama 8B, is also has a high correlation score with humans, I think. Yeah, 83. So about the same as Claude. Yeah, this result, I think, is, I wanted to highlight it just to show that even between LLMs, there's some variability, about the same variability as between LLMs and humans. But this also means that like the variability that exists, as long as your model is strong enough, is kind of controlled, and it's not going to be all over the place. It's still going, the correlation is still going to be on the high 70s, 80s. That's about it. I think we covered all the results. If people have any questions now, just to close the paper, now it's the time.
I don't have any currently. I'll message you later.
Fine. Yeah.
What are you working on right now? Or like next or whatever?
Data attribution. Well, there's some people that were here, or that are here as well. So in the summer, we're going to have the the little like maths at home.
Matt's at home.
On,
ASAP camp at home kind of thing.
yeah, on a little server, and in that I'm going to be doing SAE interpretability with a bunch of people and data attribution with less people. But on my own time, I'm only doing data attribution at the moment on the emergent misalignment results.
Cool. Wait, is that the same one as where when it was like steering something towards owls or something? Or is it a
So
different?
that's the most recent, let's say, kind of variation of that. But we are still on the old variation where you train it on bad medical advice and it starts to want to rule the world.
Right. Cool.
Okay, so it seems like people are exiting now. I mean, they've been exiting. So I think I'm going to stop the recording if I remember how to do it.